Today we're going to be continuing with Chapter 7, and we're going to be looking at Section 7.2. 7.2 is on estimating a population mean, so we'll be continuing our work with confidence intervals, except this time it's going to be talking about estimating population means instead of population proportions. Okay, as we kind of add this second type of confidence interval, one of the issues that you face is being able to determine which type you're working with. So in each problem, when you approach a problem, my recommendation is to read the question and locate what I call the construct or find statement. So somewhere in the problem, it's going to tell you what you're going to be asked to do. So you're going to be asked, like on this one, to construct a 99% confidence interval estimate of the proportion. So if you find this sentence located in the problem and focus on that, that's going to tell you exactly what type you're going to be doing. So this would be a proportion type. So it would be like the ones we've been doing in the last couple of days of lecture. This one, if you look at the construct or find statement, it says construct a 90% confidence interval estimate of the mean weight loss. So here, instead of proportion, we're going to be talking about a mean type. Okay, so this is a chart that I've put together. This is available on Canvas under the module and also on the overview page. If you click on that, it's the confidence interval study guide page. And so what you have is you can see that there are, at this point, there are going to be three different types of confidence intervals. The first was the proportion type. So the best point estimate for that was p hat. We used some of the values that we needed were p hat, q hat, n, and our z critical value. We had these as our requirements. We had this as our margin of error formula. And we wrote our confidence interval using the p hat, and then we had our interpretation statement. So now moving on, today we're going to be looking at these two types because they kind of go together. And the best point estimate when you're working with the mean is no longer p hat, it's x bar. Because if you remember, x bar is one of our unbiased estimators that approximates or estimates the mean or targets the mean as of the word we use. Okay, the values that we'll be needing for this type of problem is going to be the sample size, the standard deviation, the mean, and our t or z critical values. We'll talk about that today. As far as our requirement checks, you can see those listed, and again, we'll talk a little bit more about that. And you've got different margin of error formulas depending on the different types that you have. Both of these types, you do x bar minus the error and x bar plus the error to get the endpoint. And we actually still use this same interpretation statement as well. You can kind of see how what we're going to do today parallels what we've done with the proportions. Okay, so like we said, the main goal of the section is to present methods for using a sample mean to make an inference about the value of the corresponding population mean. So again, we're going to be studying a sample and trying to draw information and conclusions from that sample that will be true for the population itself. Okay, so the three things we'll talk about are the point estimate. So the best point estimate is the x bar. So just like p hat was the best point estimate for estimating the population proportion, x bar is the best point estimate for estimating the population mean. We're going to talk about confidence intervals and constructing those, and then we're going to look at sample size. So in this section, you're not going to have p hats and p's. You're going to work with mu, which of course is the population mean. N is your sample size. X bar is your sample mean. Capital E is still your margin of error. And lowercase s is going to be your sample standard deviation. Okay, as far as our requirements, we're going to keep the same first requirement, and that is that we're working with a simple random sample. We'll assume that to be true. And then the second one is that either we know that the population is normally distributed or our sample size is greater than 30. So we have to know one or the other of those. Okay, so it's important to know whether we're working with a t or a z critical value. And so I put this flow chart together to kind of help us decide. So the first question we're going to ask is kind of that requirement that we saw here. Is it true that it's normally distributed or n's greater than 30? So if you answer no, then it's not really going to be able, we're not going to be able to go ahead with this problem. So you're going to say neither a z or t would be used. So looking at, if we say yes, then we want to know, is the population standard deviation known? Most of the time, the population standard deviation is not known. And so we're going to spend most of our time working about using this t critical value. Occasionally, it will be known, and in that case, you would use a z critical value. Most of the time, we just don't know that much information about a population to actually know what its standard deviation would be. But if you happen to have a problem that says, like, assume the population standard deviation is such and such, then that's going to be an indication that you could do the problem with the z critical value instead of the t critical value. Okay, so here's a couple for us to talk about. The first one, we've got n equals 23 and sigma is unknown, and the population appears to be normally distributed. So it is normally distributed or n greater than 30, so we can kind of proceed this way. Sigma is unknown, so if it's unknown, then we're going to have to use a t critical value for that one. The next one, n is 25. Sigma is known. The population appears to be normally distributed. So in this case, because it's normally distributed and the population standard deviation is known, we would use a z critical value. Okay, the next one here, we've got n equals 6, but the population appears to be very skewed, so we're not able to satisfy either of these two requirements. So this would be a neither on this one. And then the last one, n is 40, so we're able to fulfill one of the two of these. It doesn't matter that it's skewed because it's greater than 30, we're okay. So we'll go down here. The population, the standard deviation is unknown, so that tells me that I'm going to have to use a t critical value. So being able to decipher this is very important, so I would learn this flow chart. Okay, for our margin of error, we're going to calculate the margin of error when sigma is not known. And remember, I said that's the case that we're going to deal with most. We calculate the margin of error by finding a t critical value. Then we're going to use s, which is the sample standard deviation, divided by the square root of n, which is the sample size. And we'll talk about this degree of freedom in just a minute. All right, so with these t critical values, they work very much like a z critical value, and I'm going to go through and show you how to find those, excuse me, with one exception, and that is that we have what's called a degree of freedom. Because the t distribution is not one curve like a normal curve is. It's a family of curves. So the degree of freedom basically helps you identify which family member you're using. The degree of freedom is always going to be n minus 1. So your sample size minus 1 will be your degree of freedom. As far as rounding, our rules with rounding are that if we work with an original data set, meaning that you are provided all 30 or 40 or 100 data values, then we're going to round our confidence interval limits to one more decimal place than whatever the data set has. So if the data set had one decimal place given, then we're going to round our limits to 2 decimal places and so forth. If we're provided summary statistics, which means they already give you the X bar and they give you the S and they give you all of this, it's already calculated, then we're just going to be consistent with that and round it to the same number of decimal places that was used for the sample mean. And usually the mean and standard deviation will be given to the same decimal place. Okay, so we're going to be working with what's called the student t-distribution. A lot of times that's just referred to as the t-distribution. That's what you'll hear me refer to it as. So if we were to basically standardize and get the our formula for the t-distribution here, it's going to be x bar minus the mean divided by the standard deviation over the square root of n. And here we're going to be using S instead of sigma when we do that because we're going to be working with the T. And I always tell my students, just remember that like S and T go together in the alphabet. And so anytime you have your S given, you're going to work with a T critical value. So they go together there. Okay, so this is an overview of this student T distribution. We use this when sigma is unknown. So if sigma is known, then we would use as a normal distribution. If sigma is unknown, we're going to use this T distribution. So when sigma is unknown, we're going to have to use S as a replacement for sigma. So if sigma is not given to us, then we're going to have to use S in the place of that. And when we use S, if you recall, the sample standard deviation is not one of those three unbiased estimators. Back in section 6.3, we talked about the fact that that X bar was an unbiased estimator, that P hat was an unbiased estimator, and that S squared, or the sample variance, was an unbiased estimator. But S itself is not an unbiased estimator. So as a compensation for using something that's not an unbiased estimator, we have to use this T distribution to compensate for that. So we have slightly larger confidence intervals because we're using something that's not a truly unbiased estimator. So we're going to use this student T distribution to compensate for that. So you can see here that we have the normal distribution is in green, and then for each one of the degrees of freedom, which is n minus 1, you get a slightly different curve. So the closer n gets, or the larger n gets, the closer the graph is getting to that standard normal distribution. Okay, so as n gets very large, the T distribution becomes essentially the normal distribution when we look at that. It does have similar characteristics to the normal distribution in that it's bell-shaped, symmetrical about the mean, never touches the x-axis, and the mean, median, and mode are going to be 0. And like we said, as n increases, the T distribution approximates the normal distribution. So it's a family of curves based upon the sample size and therefore based upon its degree of freedom. Okay, so we want to talk about finding these critical values. The process is the same, except if you recall, when we were talking about Z critical values, we memorized values for 90, 95, and 99. Those values only work for Z's. You cannot memorize T's because the problem is it's going to be different for every sample size because of the degrees of freedom. So you're going to have to find everyone and work it out. So here we're going to start. We're going to draw our curve. It looks like a normal curve, but it's actually a T distribution. We're going to find our 95%, so we're going to put the 95 in the middle here. So that leaves 0.05 that I'm going to divide between the two tails. So I have 0.025, and I'm going to find this. Okay, so what I'm going to do to find this is instead of doing inverse norm, I'm actually going to do inverse T. So you should be able to find inverse T on that same table just below inverse norm. You'll see inverse T. So that's under the second vars under your distribution menu. So you'll find inverse T. You're going to still do the area to the left, but instead of doing the mean and standard deviation, you're actually going to do your degree of freedom. So here I'm going to do inverse T. My area to the left of this line here is add these two together, and I get 0.975. And my degree of freedom is 15 minus 1, or 14. Okay, so if I put that in my calculator, what I'm going to get is 2.145. Okay, if you happen to not have inverse T on your calculator, don't panic because there is a simple way to do this. If you happen to not have that, then you're going to need to work with the table. This is, you can print this off from here. It's also on Canvas, or if you can't find it, just email me and I'll send you a copy of it. But this is a table that you're going to have to use. So if I'm looking with this, if I'm going to do that, I can look at it either way, area in one tail or the combined area in two tails. It's the same column. So looking at this example here, I have 0.025 in one tail, or if I combine those two together, it would be 0.05. So I'm going to be on this row, this column here, and my degree of freedom we said was 14. So if I go down to row 14 and look over, there's that same value that our calculator gave us. So it's a very easy table to use, but definitely if you don't have that inverse T function on your calculator, then you need to get a copy of this table to use. Okay, so I have 3 here for you to practice. So would like for you to pause this video and practice finding the critical values for each one of these, and then check your work on the next slides. Okay, for this one, when you draw this out, we want to put 99% in the middle. So that leaves me with 1% that I'm going to split between the two tails. Okay, so when I go to set this up, I'm finding a t, so I'm going to do inverse t. The area to the left of this would be 0.995 because I'm going to add both of these areas together. And my degree of freedom is 1 less than my sample size, so I should get 3.707. One thing I didn't really say is that with t critical values, we tend to round those to 3 decimal places. And if you needed to find that on the chart, here you would go back to a degree of freedom of 6 and 0.01, and so there's the 3.707. Okay, the next one, if we're going to do a 95%, we'll do 0.95 and we'll put 0.025. So my t here is going to be inverse t. The combined area to the left on this one is going to be adding those two together, so 0.975. My degree of freedom is going to be 24. So this answer would be 2.064. And then the last one, if we're doing 90%, I have 10% that I'll split, so that leaves 0.05 in each tail. So I'll do the inverse t of 0.95 and 39. So I get 1.685 for that. One thing, if you're doing this on the table, I want to go back to the table for just a minute. And it actually doesn't show on here, but it only goes to it at some point it starts kind of skipping, and it doesn't list every single degree of freedom that you could possibly have. So what you have to do is, if you're using the table, then you just need to pick the closest one. And so even though your degree of freedom here would be 39, on the table you would need to use 40 for that. So just understand that if you're using the table for very large samples, you're going to have to use the closest one with that. Okay, here are our steps for constructing the confidence interval. You'll see that they're very similar to what we've done before. We're going to, first of all, start out by locating the find or construct statement and use that to determine the type of confidence interval that we're working with, whether it's a proportion or a mean type. Verify the requirements that you have. Identify any values that are present in the problem. Find the margin of error using our formula here. Write our confidence interval, and in this case we're going to use these X bars instead of P hats because we always want to use our unbiased estimator, and X bar is our unbiased estimator, so we're going to use that to build our confidence interval. We've got our rounding rules kind of reiterated, and then don't forget to write your interpretation statement. Okay, so here's an example that I want us to go through. This one, a clinical trial was conducted to test the effectiveness of the drug Zopiclone for treating insomnia in older subjects. Before treatment with Zopiclone, the 16 subjects had a mean wake time of 102.8 minutes. After treatment with Zopiclone, the 16 subjects had a mean wait time of 98.9 minutes and a standard deviation of 42.3 minutes. Okay, so assume that the 16 sample values appear to be from a normally distributed population and construct a 95% confidence interval estimate of the mean wake time for a population that has taken the Ziplicon treatments. Okay, so looking at this one, we're going to start here with part A. I've got a couple things we want to identify. Here's our sample size. Okay. We're mainly concerned with after the treatment. So this is going to be our X bar because that's referring to the subjects. And this is actually an S. A lot of people get confused because it says standard deviation. There are two types of standard deviation. There's sigma and there's S. You have to read this and decide which one it's giving you. So unless it says population standard deviation, then it's probably going to be an S because we mentioned that very rarely do we actually know the population standard deviation. If I'm looking at this, another thing is that this standard deviation is coming from the 16 subjects that are being studied. So if it's coming from a sample, that's another indication that it's an S. Okay, so we want to locate our construct or find statement. So here's our construct statement. Construct a 95% confidence interval estimate of the mean. Okay, so that tells me that it's going to be this type we're looking at today, the mean type. So I want to identify my values, which I've done here, and then I want to look at my requirement check. Okay, so the requirement check, we said it needs to be a simple random sample, and I've said we can just assume that to be true for what we're going to be doing in this class. And then we also need to know that it's normally distributed or the n's greater than 30. Well, our n is not greater than 30, so we need to dig a little deeper and make sure that it tells us somewhere that it's normally distributed, and it does here, so we can check that off as being a requirement that's fulfilled. Okay, so we need to decide too, is sigma known or is it unknown? Okay, so the only standard deviation they give me is this 42.3, and that's an S. It's not a sigma. So this is not going to be known. And so that means I'm going to need to use a T critical value. All right, so we're kind of getting ready to get started here. Our margin of error formula is T alpha over 2 times S over the square root of N. So I know what S and N are. I just need to find this critical value here. Remember, we can't just go by the memorized values for the T's. We're going to need to actually find that. So if this is a 95%, we just went through practicing finding these. So this would be a T critical value that we're going to need to work with here. So I'm going to do inverse T or use the table, whichever you have to do, inverse T of 0.975. And my degree of freedom is one less than my sample size. So that's going to be 15. So that's going to give me 2.131 for my T critical value. So this will be 2.131. My S was 42.3 divided by the square root of N. N was 16. So my margin of error is 22.54. So the margin of error looks a little bit different on these problems. It may be a little bigger value than what you had dealt with in the previous problems. Okay, so this is the first part of what we've got to find. The next thing we want to do is to actually write that confidence interval. So we're going to do X bar minus the error. We're going to put mu in the middle. So X bar we said was 98.9. And I'm actually going to take some of this off so that I have room. Hopefully you already have that from the notes. Okay, so So when I simplify this part, I'm going to get 76.4. And then when I simplify this part over here, I'm going to get 121.4. I want to round it to one decimal place because that's how many decimal places my mean was given to. And so I'm going to round that to one decimal place. So this would be my answer here for this. Okay, so what does the result suggest about the mean wait time of 102.8 minutes before the treatment? So if we look at this, our mean wait time here, 102.8 is what it was before the treatment. After the treatment, it shows that we're with 95% confidence, we would expect it to be between these values here. So because of that, this is fitting right in the middle. So it actually appears that there was no effect from these treatments that were being applied because the interval, the average or the mean that we had before fits right in the interval that we are saying now for those that took the treatment. Okay, so it does not appear that it would be effective because of that. So the confidence interval includes the mean that was measured before the treatment, so the mean could be the same after the treatment and suggests that it does not have a significant effect. Okay, on the calculator, we had looked at doing the proportion type, and for that we went to stat, test, and then one proportion z interval. For this type, we're going to go to stat, test again, but we're going to go down to number 8, which is t interval. This time you can choose between data and stats. Data would be if you're given like all 30, 40, 50, 100 data values. Stats is when you're given like the summary statistics. So we were told that the mean was 98.9, the standard deviation was 42.3, and the sample size was 16. We wanted to do a 95% confidence level. So when you press enter and calculate that, here is your interval that it's going to report, and that's consistent with what we had calculated by hand. Okay, here's a data set that I would like for you to take the time to put in your calculator, and we're actually going to compare the two restaurants once you've had some time to get that entered in the calculator. Okay, so I had asked that you enter this data in your calculator. So if you will make sure you've entered one column restaurant, the first restaurant, let's call it restaurant X in L1 and restaurant Y in L2. So what we're going to do is we're going to go to stat, over to test, and then we're going to go down to number 8, which is T interval because we don't know the population standard deviation. Here we're going to choose data because we're going to use the data set, and we're going to start with L1. We want a 90% confidence level, and we're going to calculate. So here's the confidence interval for this particular data set. So keep that in mind, write that down, and then we'll use that for comparison. If we go and we look at, do the same thing, except this time we're going to do for L2. Okay, then you can see that while they do overlap slightly, restaurant X was the one that had higher values here, and restaurant Y has lower values to look at with this. So this one's talking about the mean drive-through service times at dinner. So it seems that restaurant X is going to have a little bit longer times than restaurant Y, even though they do slightly overlap with that. Okay, on this one, we've got 12 different video games showing substance use or observed. The duration, times, and seconds of alcohol use were recorded with the times listed below. The design of the study justifies the assumption that the sample can be treated as a simple random sample. Use the sample data to construct. So here's our construct statement, a 95% confidence interval estimate of mu. So we're going to do a confidence interval of the mean is what we're looking for here. So if we look at this, here we have the data set. So what we're going to need to do with this, even if we're going to work it out by hand, is we're going to need to get the data values from this. So if we go to put it in the calculator, one of the things we've got to do is we've got to check our requirements. So we were told it was a simple random sample. But we also need to know, is it normally distributed or is n greater than 30? So if we look at this sample, clearly we don't have more than 30 data values. So what we need to do is we need to look and make sure that it is at least approximately normally distributed. And we can do that through a normal quantile plot. So just as a reminder, you'll go to second y equals, which brings up your stat plot. Choose the very last graph here and then do zoom stat, which is zoom 9. And because it doesn't line up in a straight line, then that tells us that our population here is not normally distributed. Since it's not normally distributed and it's not greater than 30, we actually aren't able to go ahead with this problem. So if we can't fulfill these requirements, then we have to just stop with it. Okay, sometimes you're going to be asked to find your X bar and your margin of error when you have been given the confidence interval itself. We looked at some of these using for the p hat and the X bar, so it's very similar. To find the X bar, it's in the middle of the interval, so you'll do the upper plus the lower divided by 2. And then for the margin of error, you're going to do the upper minus the lower divided by 2. So like in this one, if you're given this as your confidence interval, and notice that mu is going to be in the middle of these for the mean. So if you have that, you're going to add them together and divide by 2, and you'll get 9 as the mean. And then you'll subtract and divide by 2, and you'll get the E, or the margin of error. Okay, so last thing today is I want to look at sample size as it relates to population mean. So we've got these same different symbols that you need to be familiar with. Okay, our last sample size formula is going to be n equals z alpha over 2 times sigma divided by the margin of error, and all of that squared. So a couple just notes, always round up when calculating sample size. So we talked about that in the previous lecture. One of the key words is how many. So if it asks you for how many, then you know you're looking for a sample size. Within indicates margin of error. And then occasionally your population standard deviation is not going to be known. And when it's not known, you're going to use the range rule of thumb to approximate it. And the range is going to be the range divided by 4, which if you recall, the range is maximum minus minimum. And then we'll divide that by 4. And so that's going to be our formula for approximating the population standard deviation. Okay, so here's an example. Assume that we want to estimate the mean IQ score for the population of statistics students. How many, so that tells us it's a sample size problem, how many statistics students must be randomly selected for IQ test if we want 95% confidence that the sample mean is within, so that's an indication of our margin of error, within 3 IQ points of the population mean. Assume the population standard deviation is known to be 15, so that would be my sigma. So my formula for this is z alpha over 2 times sigma divided by the margin of error, and then everything squared. Okay, this is a z. So when it's a z, we can go back to our memorized values. So I need the z that corresponds with 95%. So that's going to be 1.96. My population standard deviation is 15. My margin of error is 3. That we do not move a decimal with these because it's not a percent, it's an IQ score. And then we're going to square that. So I get 96.04. And even though that's just barely above 96, we still round it up to 97. Okay, occasionally we do get a scenario where sigma is known, so I do want to go through one example here. If sigma is known, then the main difference is we're going to use z alpha over 2 instead of the t, and we're going to use sigma instead of s. So if sigma is known, then we want to use it, and we'll have that in our formula and the z that goes with it. So z and sigma go together, and s and t go together. Okay, here we're going to use the 15 birth weights to construct the, and we want to construct a 95% confidence interval estimate of the mean birth weight for all girls by assuming that sigma is known to be 2.9. So here you can see sigma, they're giving us the information about sigma. They're actually already giving us the summary statistics as well, so it's really not necessary to go through and put this in the calculator to do this problem. We're going to assume on this one that it is normally distributed. We're not going to go through and check with this again. So we're going to assume it's normally distributed or n greater than 30. You do need to verify that in different cases, but you can look real quickly here. And it's not exactly lined up straight, but it is pretty close. So just do your normal quantile plot to verify that. Okay, so then for our margin of error, it's going to be z alpha over 2 times sigma divided by the square root of n. Okay, so our z alpha over 2, the nice thing about the z's is we can always go back to the memorized values. So this would be 1.96. Our population standard deviation was the 2.9, and our sample size was 15. So we get 1.47 for that margin of error. So we're going to build our confidence interval by looking at x bar minus the mean, sorry, x bar minus the error. Have mu in the middle and then x bar plus the error. So I'm going to kind of go up here where I have a little bit more room. X bar was 30.9. We're going to subtract the error from that. And then here we're going to have 30.9 plus the 1.47. So I'm kind of running out of room, but that comes out to be 29.4 and 32.4. Okay, so that would be our confidence interval for the mean using this sigma that's known. So it really just depends on whether sigma is known. If it's known, you use the z. If it's not known, then you have to use the t and find that. But that's the interval that we should have for this one. And we do round to 1 decimal place because looking back at their data set, our data set's whole number, so we want to go 1 decimal place more than that. If I want to do this on the calculator, I've got a couple screenshots here to show you. You'll go over to that same test menu, except this time use the z interval. So here you'll use, when sigma is unknown, you're going to use this t, but when sigma is known, you're going to use the z for that one. So this particular one, you could have actually chosen either one. If you wanted to enter the data, then you'd have chosen this one. If you wanted to just enter your summary statistics, then you choose the stats one. And so you'll put in your mean and your standard deviation if you're doing that way, and then you get your and calculate, and you can see here's the interval that we came up with. Okay, so just to summarize, the proportion, you use 1 proportion z interval. Mean with sigma unknown, you use the t interval, and mean with sigma known, you use the z interval. So on the test, there will be some that I do expect to see your work, and I do expect to see you calculate all the parts to the confidence interval. There will be others that you will be just simply allowed to use your calculator, and I'll be focused more on the interpretation of the confidence interval and not actually getting the interval itself. So there will be a combination of the two, so expect to have to show your work finding the margin of error and not to be able to do everything on your calculator. Okay, here's one last one for you to try if you would like to try this. Okay, on this one, we've got randomly selected statistics. Students of the author participated in an experiment to test their ability to determine when 1 minute or 60 seconds has passed. 40 students, so that's going to be my n, 40 students yielded a sample mean. So my sample mean would be my x bar and a standard deviation. So this standard deviation reverts back to the 40 students. So this is going to be an S that I'm going to be using here. So that means I'm going to have a T critical value. Remember, S and T go together. Find the best point estimate of the mean. Well, the best point estimate of the mean is X bar, and X bar is 58.3. So that would be my answer for part A. Part B, construct the 95% confidence interval estimate of the population mean. So since it's this is my construct statement. So I'm doing the population mean, so that means I'm going to have to check the requirements for the mean, which is simple random sample, and either normally distributed or n greater than 30. So our sample size was 40, so I'm good with that. So I'll move on to calculating my margin of error. So I'm going to have T alpha over 2 times S over the square root of n. So to find my T, I've got to find that for a 95% confidence interval. So you can see that these, you get kind of used to drawing these out. So I'm going to have the inverse T. I need the area to the left of this line, which means I'll add these two together. And then I'll have to have my degree of freedom, which is 39. So I'm going to get 2.023. So I'm going to have 2.023. My standard deviation was 9.5, and I'll divide that by the square root of n. So I'm going to have 3.039 for my margin of error. Next, I'm going to add and subtract my margin of error to my sample mean. So my sample mean was 58.3, and I'm going to subtract from that 3.039, and then I'm going to add that to it. So when I simplify that, okay, so this is my confidence interval. So we would say we are 95% confident that the interval from 55.3 seconds to 61.3 seconds actually does contain the true value of the population mean of statistics students that participated in the experiment to test their ability to determine when 60 seconds has passed. Okay, based on the results, is it likely that their estimates have a mean that's reasonably close to 60 seconds? 60 falls within this, so yes, it is reasonably, it is likely that their estimates have a mean that's reasonably close to 60 seconds. Okay, so I have these three problems here. I'd like for you to take a minute to decide which type they are. We're not going through and solving them. You've got plenty of examples at this point of how to solve them. I just want you to focus on which type they are. So proportion, mean with sigma known, or mean with sigma unknown. So pause this and try it, and then see what your answer should be. Okay, as I said, you always want to find your construct statement. So this one says we're going to construct a 90% confidence interval estimate of the mean. So because it's a mean one, you need to go back and figure out whether it's mean with sigma known or unknown. So here my standard deviation is referring back to these 40 people. So this is going to be a mean with sigma unknown. Okay, on the next one, here's my construct statement. And this time we're going to be constructing a confidence interval estimate of the proportion. So this is going to be a proportion type problem. Okay, here I've got my construct statement, a 90% confidence interval estimate of the mean. So I need to look back and see which type it is, whether sigma is known or unknown. So it says assume that the population mean is, this should actually be population standard deviation, and that's a typo on my part. Population standard deviation is the 0.366. So if in fact this is standard deviation here, then sigma would be known, and therefore it would be a mean with sigma known. Okay, and again, that was my fault for having typed that wrong. Okay, I'm going to show you very quickly how to do this on StatCrunch. Okay, so I'm over here in StatCrunch, and I've pulled up some data for body data for males just to demonstrate here. So if you go to Stat and then you're going to choose from between Z-stats and T-stats. So since this is a sample that we're working with, I'm going to do, and we don't know the population standard deviation, I'm going to do T-stats, and I'm going to choose one sample. And since I have data, I'm going to choose with data. Let's look at the confidence interval for platelets. And we're going to come down here and do confidence interval. We'll do the 95% and compute. And so then it gives us the limits of our confidence intervals here, the upper and the lower confidence interval limits for that. If I don't have the data, then what I can do is just go and just choose, just like with the calculator, I'm going to choose with summary. And so I'll enter my sample mean. So on one of our previous problems, our sample mean was 58.3, and the sample standard deviation was 9.5, and the sample size was 40. So if we do a confidence interval, and this was the one about the time with the statistics and the time, then our confidence level that it asked us to do was 95. And we'll compute that. And so here is that same interval that we computed by hand. So the StatCrunch is going to give you the options to do these same things. Okay, so that concludes today's lesson. If you have any other questions, please let me know. Reach out to me during office hours or some of our Zoom sessions, and I'll be glad to answer your questions. Thank you, and hope you have a good day.